Part 2 of lesson 44 is the period of pendulums. And please go to YouTube and watch. There are some amazing videos on pendulum wave demonstration. This is a good one, but there's a whole bunch of them that are super interesting to watch. I think we watched one already, but yeah, watch this one too, the Ghent Light Festival. So watch those and you'll discover some interesting things about the periods of pendulums, and then come back to this. And the first part, it talks about Galileo. He's watching lanterns in the church, and he noticed that they were swinging. And it says Galileo noticed that all the lanterns were the same mass. The length of the chain they were dangling from seemed to change how fast they were swinging. And what Galileo found, and this is where we're really missing being in class here, because we would do a lab on this, and it's a straightforward lab, but it teaches you some things that you probably didn't expect, like what affects the period of a pendulum. So here's a pendulum going back and forth, back and forth, back and forth. What affects that? Does the mass affect the period of the pendulum? Does how much you pull it back affect the period of the pendulum? If you look at the formula, that is the formula on your formula sheets for the period of a pendulum. T equals period equals 2 pi times the square root of L over G. You will notice that neither of the two things I just talked about, the mass or the amplitude, neither of those appear in the formula, so neither of those affect the period, which should be interesting. It doesn't matter how much mass you put on the end here, the period will be the same. The only things that affect the period, how long it takes it to go back and forth, and let's just discuss that quickly. The period of a pendulum is back and forth. That's one cycle of the period. Okay, so it's not just one way, it's back and forth. So the period of the pendulum is affected by the length, L, of the pendulum and gravity. So if you want to change the period of a pendulum, you have to change the length of the string, or you have to do the experiment on the moon, for example. Like gravity is different. Okay. So yeah, that's really it. And then we can do example number 4. Determine the period of a pendulum that is 12.5 meters long. Since we have no reason to think otherwise, we'll assume it's on Earth. Period equals 2 times pi times L over G. Plug the numbers in. Again, the negative is not only irrelevant, but inconvenient in this case, because you put a negative in there, you can't calculate the square root of a negative number. So leave that out, and you're going to get 7.09 seconds. So that's how long it takes to go there and back. 7.09 seconds. That's a pretty long pendulum, 12.5 meters. Where this gets a little more interesting is when you're asked to calculate something other than the period, just because of the nature of the formula. In other words, it has a square root in it. We decide to measure gravity in a particular location on Earth. We use a 2.75 long pendulum and find it has a period of 3.33 seconds. Determine the acceleration due to gravity in this area. There's 9.81, that's kind of your average gravity for the planet, but since the planet is not perfectly circular, then it changes a little bit, like not a lot, a very small amount. So in this case, we're solving for G. And it's to your advantage to manipulate the formula. Personally, I wouldn't. I'd just plug the numbers in and solve for G. But just to get the experience of manipulating the formula, let's do that. So let's manipulate it for G. And anytime you're asked for a variable, to solve for a variable, and that variable is under a square root sign, the best thing to do right off the bat is square both sides. And be very careful here, because it means you have to square everything. t squared. This applies to the 2. It applies to the pi, and then it applies to this as a whole. It can apply to them individually, but it's best to just do it as a whole. So t squared equals 4 pi squared times L over G. When you square the square root of something, you just get rid of the square root. So this square has the function of eliminating this root sign here. And then solving for G is pretty straightforward. Put the G up here, put the t squared down there, just do the old switcheroo, and you're going to get G equals 4 pi squared L over t squared. Plug your numbers in and get your answer. Don't forget to square the pi. Don't forget to square the 3.3. The answer turns out to be 9.78 meters per second squared. Which seems like a pretty reasonable answer, because we're just talking about somewhere else on Earth it's going to be very, very close to 9.81. All right, and if you, before we do number 6, if you just did decide to plug the numbers in, then let's just go through that really quickly, just for those who, ooh, it's moving slow. For those who don't care to manipulate formulas, then it's just 3.3 equals 2 pi 2.75 over G. And then you more or less follow the same procedure, don't you? Because you've got to get rid of this square root. So the first thing you're going to do is square everything. So you're going to end up doing all the same things, and then you're going to go from, and then you're going to, once you square this, you're going to move the G up here and then divide by that. So whichever way you want to do it. All right, and the last example is determine the length of a pendulum that would have a period of 1 minute. Okay, think about that question before you do it. Period of 1 minute. It takes 1 minute to go. Is that going to be a really short pendulum or a really long pendulum or just a medium? It's going to be a long, long pendulum. It takes 60 seconds to go back and forth, 1 full minute. This is going to be a huge pendulum. T equals 2 pi L over G. If we're manipulating that formula for L, we're going to do the same thing. And this one's even a little easier because you're just going to move the G up to the t squared and then divide by 4 pi squared. So you're going to end up with L equals t squared G over 4 pi squared. Plug your numbers in. The t is 1 minute, but you have to have that in seconds. So it's going to be 60 squared and once you plug that in, you're going to end up with 895 meters. So that's an intensely long pendulum. That's almost 10 football fields, well, almost 9 football fields. Crazy long. Well, actually, since we measure football fields in yards, it's actually more than 9, because a meter is slightly more than a yard. All right, that ends lesson 20. 44.